Welcome to this online demonstration of some of the features of TreeAge Pro. The goal of this demonstration is to introduce the concept of Markov modelling using a simple example, and then we'll examine the elements of the simple Markov model. This demonstration will use the 2013 version 1.1 of TreeAge Pro. First, I'm going to give a brief overview of the concept of Markov modelling, which will include introducing some common terminology, and then we'll go into more details about what those terms mean. In a standard decision tree structure, it's difficult to show disease progression into the future without creating an extremely large model. A Markov model, or state transition model, will allow us to look at events that recur over time in a simpler, more concise way. A Markov model will break down the overall progression into individual cycles which can repeat over an individual's lifespan. Each cycle starts with a cohort divided among a set of mutually exclusive health states. In each different health state, we model the events and progressions that can occur within the cycle. These events determine whether portions of the cohort will stay in that health state or progress to different health states. Therefore, the cohort is likely to start each cycle with a different distribution among those health states. State rewards, such as cost and effectiveness, are input into the model for each health state. These rewards are accumulated for the percentage of the cohort that starts the cycle in that state. Transition rewards are associated with one-time event, such as being admitted to an inpatient into hospital in a certain health state. The transition rewards can be assigned to any event at any node to the right of the health state. Here we have the health state alive, and the transition rewards can be assigned here. The total state and transition rewards for every state and every cycle are accumulated, and they become the overall expected value for the Markov model. The Markov model can be integrated into larger models for decision analysis. The simple model we have open is example 7 from the healthcare training examples. We will use this example to talk through the standard elements in a Markov model, which are the following: a Markov node, indicated by this M in a circle, and everything to the right of it. So all these branches here. The set cycle length, which is defined here at the Markov node. Mutually exclusive health states, which in this model are alive and dead. Rewards, defined at each health state. And transition subtrees, which is this element here. Markov models follow a hypothetical cohort as it progresses with time. Markov model starts at the Markov node and covers everything to the right of that node. The cohort is homogeneous, so there's no individual characteristics that we're tracking. The cohort has a total size of 1, but it will be split into different proportions that follow different paths or health states through the model. This results in overall expected values for a typical person. For each health state, the proportion of the cohort in each state is split further to reflect the many events that can occur in the cycle. At the end of a cycle, the cohort is returned to the health states in different proportions depending on the transition probabilities to start the next cycle. Here we see that initially this cohort is all alive and there are no elements of the cohort who are dead. The overall model is divided into smaller time periods or cycle lengths relevant to the problem we are considering. We never actually define or use units to define the cycle length, but it's nonetheless important for the following reasons. All of the probabilities and rewards must have values which are consistent with the cycle length, be it 1 day, 1 month, or 1 year. The model is usually run for a specific number of cycles, for example 20 one-year cycles. In Markov models, there's a built-in keyword called stage, which we see here at the Markov node, and it's used as a reference to the cycle count, and stage can be used to represent any cycle length. For the first cycle, underscore stage equals 0. So if we want 20 cycle lengths, then the first is when underscore stage equals 0, and the last is when underscore stage equals 19. Each health state describes the current health state of an individual. So for example, healthy, sick, or dead. In this model we have 2, alive and dead. Each state is a collection of events which may happen or are associated with that health state. For example, if you were in the local health state, local cancer, certain events will happen which would not happen in the well health state. Initial probabilities govern the initial distribution of the cohort amongst the health states. They're only used at the start of the model, and in this example we have all the cohorts starting as alive, so equal to 1, and none in the dead health state, so that's equal to 0. Transition subtrees and transition probabilities, which we're going to describe next, will incorporate the mechanism to move the cohort from one state to another. So this is the transition subtree for the alive state. At the end of each cycle, the proportion of the cohort in each state is recalculated for the start of the next cycle. Note that the exception is for the absorbing states, in this case the dead health state, and they go nowhere. A transition subtree exists for each health state. This is the model structure for collecting all the events that can happen within a cycle into one place. So the subtree is a collection of events that happen for that health state. For example, they could be things like surgery, screening for a test, or a stroke. Transition probabilities provide the probabilities of those events occurring within the transition subtree. Some events will drive a change from the starting health state to a different health state. So in this example, we have a transition subtree here for the alive state, and we see that the transition probability from alive to dead is 0.1, or 10%. Each Markov state has its own transition subtree, which will show where the cohort that entered the subtree can progress to based on their transition probabilities. Terminal nodes at the end of the subtree, so here we have an alive terminal node and a dead terminal node, direct the cohort to their next health state to start the next cycle. Note that absorbing states do not have a transition subtree, so that's usually the dead state is the absorbing state, because there's nowhere to progress from there. In each state, reward values accumulate per cycle, depending on both the starting health state and the events which happen in that state. Rewards would typically be cost and effectiveness, and you can see those defined here in each health state. State rewards are accumulated for the percentage of the cohort that starts a cycle in that state. For example, we can accumulate the cost of treating a person with that state's health condition, such as $10,000 per year to treat a person with diabetes. We can also accumulate utility associated with the health state to represent effectiveness. These are these values here. For example, if a person is in bad health, they might only accumulate 0.8 of effectiveness rather than accumulating 1 for a person in good health. Rewards may differ per cycle, and the Markov model gives us the options of setting different values for initial, so here we have the initial cost for the alive state, incremental, so that's for every subsequent cycle, so this is the incremental cost, and then the final one-off cost, usually in the last cycle. Transition rewards are accumulated for the percentage of the cohort that starts a cycle in that state and that pass through a specific event in the transition subtree. Rewards are accumulated until all the cycles are finished. We have now explained all the main features and the terminology associated with this very simple Markov model. We note that in a previous demonstration we've explained how to create a Markov model from a state transition diagram. The next demonstration will show how to build the Markov model, example 7 that we have open here. To recap, this demonstration has covered the concepts of a Markov model and the elements that make up the simple Markov model. Thank you for watching this online demonstration by TreeAge Software.